Hi everyone, and welcome back to another episode of Dr. Kyle Explains, your YouTube channel where we go through GCSE science content quickly and easily. Today we're going to be going over the Reactivity series. So, grab a pen, grab a paper, don't forget to give the video a thumbs up, tell everyone about it, subscribe and turn on the bell notifications, and let's go ahead and jump in. Okay, so some key points. So when metals react with other substances, metals form positive ions. How reactive a metal is depends how easily it forms its positive ion. Metals are arranged in the reactivity series to show how reactive they are. And a quick reminder, oxidation means loss of electrons and reduction means gain of electrons. Okay, so quick recap then. So a metal and an acid makes a salt plus hydrogen. So for example, if I took the metal Na, which would lose an electron and form a positive ion, and I reacted it with the acid HCl, it would make the salt NaCl plus H2. And then just to balance it up there, I'd put a 2 there, a 2 there, and a 2 there. Now, metal plus water makes a metal hydroxide plus hydrogen. So again, if I take sodium, Na, and I react it with H2O, I would make sodium hydroxide. So that's NaOH, OH being the hydroxide, and again, plus H2. And then just quickly looking at that, so I've got 3 hydrogens on that side. I'm going to put 2 there, so put a 2 there and a 2 there to balance it up. So whenever you have a metal and an acid, you make salt and hydrogen. And whenever I have a metal and water, as long as it's reactive enough, it will make a metal hydroxide and hydrogen. Okay, so this brings me to the reactivity series. So at the top we have the most reactive, and at the bottom we have the least reactive. Now you do not need to learn this list specifically, but you do need to have a good idea of where these elements would fit in. Now the elements carbon and hydrogen are added into this reactivity series because they're often used to extract the elements that are below them. So for example, carbon is more reactive than iron, so it's often used in the extraction of iron when using iron ore and then taking iron on for construction and things like that. So just to summarize then, we've got kind of the less reactive ones at the bottom. And so I often tell my classes that things like gold and silver are used in jewelry. And the reason they're used for jewelry is because they're shiny and nice, but also because they're not very reactive. We can touch it with our skin. Copper is used in our pipes at home. And so again, we don't use a reactive metal for our pipe work. Moving up, iron, obviously used in construction, which we just said, but iron will obviously slowly react with water. It's a very slow reaction. As we know, it rusts, takes a long time, and then further up it gets more and more reactive until we get to potassium, where we just put it in water and it will ignite with that lilac flame. And so very briefly, if we just take kind of water and we take acid, which we've just talked about those reactions, kind of these ones here, if we just kind of very briefly separate them, these would react violently with water, so they would fizz, they would produce lots of steam, it would be very exothermic, and in acid they would explode. And then it kind of just gets less and less reactive down here. So these ones down here up to about roughly zinc would be less reactive. Might still get a bit of fizzing with kind of calcium and things like that. Iron and things would be a slow reaction. And then with acid, they would kind of fizz. This would be producing hydrogen again and a salt. And then down here would be kind of only really reacting with high temperature water. And again, maybe producing a salt if there was a lot of heat adding to it. And then down here would just be no reaction at all, even with acid, because they're getting less reactive as you go down. Okay, so quick recap on displacement reactions then. So in a displacement reaction, the more reactive element will displace the less reactive element of a compound. So i.e. potassium plus sodium chloride, potassium is more reactive as we just saw on the reactivity series. And so potassium will form potassium chloride plus sodium. It will kick out the less reactive element. And so our symbol equation then would be K for potassium plus NaCl goes to KCl plus Na. And our ionic equation then, what we would do is we look at our symbol equation. So that's 0 at the moment. Our sodium, is positive. Our chlorine is negative. It's positive there and negative, and then it's 0 over there. And so our ionic equation is K plus Na plus goes to K plus Na. Essentially, you're just removing your spectator ions. You're getting rid of the ions that are staying the same in their charge. Then we look at our half equation. And so K is going to K plus 1 electron because it's lost an electron. So therefore it is oxidized. And then our sodium ion is gaining 1 electron to form sodium metal. And so that is being reduced in its displacement reaction. Really well done if you followed that through. Okay, so here, have a go at yourself then. Complete the word and symbol ionic and half equations for the reactions. We've got copper sulfate plus magnesium. Magnesium's more reactive, so we're going to make magnesium sulfate plus copper. So we're going to kick out the copper. Then we're going to do our symbol equation. So our symbol equation we're going to do is CuSO4. SO4 is sulfate plus magnesium goes to MgSO4 plus copper. Ionic equation then. Ionic, there we go. Right, so we look at the charges. So sulfate is always -2, so therefore the copper is +2. Magnesium's 0 there. Sulfate's -2, and obviously magnesium's in group 2, so that's +2. Copper's 0 over there. What do? You remove your spectator ions, so you get rid of your sulfate. And so for your ionic equation is Cu +2 plus Mg goes to Mg +2 plus Cu. And your half equations are going to be Cu +2 goes to Cu. So what do you have to do to that? You have to add 2 electrons to get rid of that. And so it's gaining 2 electrons, so therefore it is reduced. And your magnesium goes to magnesium +2 plus 2 electrons. The magnesium has lost 2 electrons, so it has been oxidized. Really well done if you followed that through. Okay, so last bit I want to talk about is we're going to determine the order of reactivity for the metals X, Y, and Z. And so these are obviously random metals, and we want to determine an order of reactivity for it in a 6-marker question. And so the way to do this would be to react with a metal salt or an acid. You could do either. We'll do an acid in this example. So what are we going to do then? We're going to react a metal with an acid, and what does that make? It makes a salt plus hydrogen, and so that also often gives off a lot of heat in the process. So what I would do is I would measure out, let's say 20 centimeters cubed of hydrochloric acid, and place in a polystyrene cup. So whenever you're measuring energy changes, you always use a polystyrene cup, because polystyrene cups are insulators. They keep that energy in place. Right, then we're going to do, we're going to weigh out, let's say 0.2 grams of metals X, Y, and Z. And then, really important, we are going to record the initial temperature of the acid. Okay, so we've recorded the initial temperature of the acid. Then we're going to place metal X into acid and record the highest temp reached. Calculate the temperature change. Temp change. And repeat for metals Y and Z. Then what are we going to do? Quite simply, the metal with, let's put an E on the end, with the highest temp change will be most reactive. And so essentially what we're doing here is, because we've got a metal plus acid goes to a salt plus hydrogen, what we're doing is we're taking X, Y, and Z, placing it in the acid. We know that it's going to react because it's reacting with the acid. We're recording the highest temperature, and because we know the initial temperature of the acid, you then find which one has got the biggest or the largest energy difference, and that's going to be the most reactive metal, and then you can simply put it in order of the reactivity. Really well done if you followed that through. Okay, so what we've done today then is we've explained what a displacement reaction is and why it occurs, and we've written equations for displacement reactions. We've also described displacement reactions using Arnick and Half equations, and we've identified which one's been oxidized and which one's been reduced. Thank you very much for watching. Please do go through my other videos for more GCSE science help. And remember, if you ever need help with your GCSE science, Dr. Kyle explains.